If we have a 0.9 meter long aluminum rod with a transverse vibration, a longitudinal vibration, velocity of 6,000 meters per second, which is about what we conjectured by measuring the length of the rod and the frequency of the sound in class, and this is well within 10% of the accepted velocity and the theoretical velocity for the for the velocity of a longitudinal wave in aluminum. If we're holding the rod by the middle, we'll have a node in the middle. If the ends of the rod are free, then there'll be antinodes, points of maximum deflection. This is then the fundamental mode of that aluminum rod. Now, if we have an aluminum rod 0.9 meters long, our question is, what frequency do we expect to observe? Okay, a wavelength, and let's just take a look at a picture of a typical wavelength. A wavelength looks like this for transverse vibration. For longitudinal vibration, we consider this to be just a graph of the longitudinal displacement versus position. And it's not really a picture of what the wave looks like, it's just a graph of displacement versus position. But in either case, if we have a node here and a node here, we have an antinode, then a node and an antinode. That is, a node in between with antinodes in between nodes. An antinode is a point of maximum displacement, a node is a place of zero displacement. So we have two antinodes here and here with nodes all around them. Now, this wavelength consists of 1, 2, 3, 4 node-antinode distances. So the wavelength is 4 times the distance between a node and an antinode. Okay? Now, since the wavelength is 4 times the node-antinode distance, then the wavelength is 4 times the 0.45 meters between the node and an antinode. Since there's 2 node-antinode pairs in the 0.9 meter length, the difference between node and antinode is 0.45 meters. Okay, so the wavelength is 4 times that, or 1.8 meters, from which we can easily determine the frequency. The frequency is just the velocity over the wavelength, which comes out to be 3,333 hertz. Let's contrast that with what might happen if we had an aluminum rod 0.9 meters long here with an end embedded in a concrete wall or something. And let's assume there's 0.9 meters of rod sticking out from the wall. Now, if we hit the end of this thing, it'll make a sound. Maybe not for long, because the concrete wall might well damp out the sound, but if it's good and rigid, the sound might last for a little while. Okay? So, the transverse waves in the aluminum don't propagate the way the longitudinal waves do. They don't have the resistance of the longitudinal waves. Really, you have this bulk modulus, or Young's modulus, sorry, in aluminum that determines the frequency of a longitudinal wave. What determines the frequency here is just how stiff the rod is, and that will actually change with the thickness of the rod and the length, of course. In any case, if we assume that there's a 600 meter per second velocity of propagation in this rod, what's the wavelength? Well, the concrete wall certainly imposes a node at this end. If this end is free, then you're going to have an antinode here, and it's possible for this thing to vibrate, just kind of like this. Of course, there'll be some curvature that there isn't in the pin, but it'll just kind of vibrate. I can't do it with, but kind of like this, right? Only in this direction. The wavelength will be then 4 times the length, because it's 4 times the node-antinode distance, or 3.6 meters. And from that we can calculate the fundamental frequency, which will be about 166.7 hertz. Let's look at the natural modes of vibration in a string. We're going to look once more, and we're going to look at how the natural modes compare with each other. Okay, in a string, we have nodes at both ends. Let's assume that the string is fixed at both ends, so we have nodes at both ends. And we could have a string dangling with an antinode at one end. But that's a fairly complicated situation for reasons I won't go into, except that the tension is changing over the whole length of the string, and you don't really want to get into that. Not at this point. Later on, yes. If you continue with physics, you will get into that sort of thing. Okay. If there are nodes at both ends, there's an antinode in the middle, at least one antinode. And of course, if there's exactly one antinode in the middle, then you have the fundamental mode of vibration, where the frequency is the frequency of the fundamental. The wavelength is twice the length of the string, as we've seen before. Going to the first harmonic, second harmonic, or the first overtone, the first sound of a higher frequency than the fundamental that we hear naturally in a string. The string will still have nodes at both ends, but we're going to add an antinode-node pair, so that we have node, antinode, node, antinode, node. Now there's nothing between here and here that you can do, since you have to have an antinode between two nodes and a node between two antinodes. This is the next possible stable configuration of the string, or the next possible harmonic of the string, next possible resonance. In this case, the wavelength, well, we can trace out a wavelength that's equal to the length of the string, as we've seen, so that the frequency turns out to be twice the fundamental. Okay, and it's not hard to see why that's the case. We've seen it before. The frequency here is the velocity of the wave divided by the wavelength, which will be velocity over 2L. Frequency here will be velocity over L, which gives you twice as great a result as you have here. We're assuming, of course, that the string in all cases is under the same tension and has the same mass density. If we go on, we get the second overtone. We add another antinode-node pair, we get another hump in the configuration of the string, and you're familiar with this by now. The wavelength is 2/3 L. The frequency will be the velocity divided by 2/3 L, which is 3/2 the velocity divided by L, and it turns out that's 3 times the fundamental frequency. Now, what are the ratios of frequencies that we naturally hear? When strings are plucked, we have all these frequencies at once, as you can see from the wave simulation. Well, the natural frequency ratios are just 2:1, 3:2. Of course, 3:1 is also natural, but let's just list the consecutive ratios, 2:1, 3:2. It's fairly obvious that this pattern will continue on to where we have 4, 5, 6, 7, and 8, and so forth, of these harmonics, of these antinodes across the string, which will give us 4, 5, 6, 7, and 8 times the fundamental frequency, which will give us ratios. We got 2:1 and 3:2. The next one will be 4:3 and 5:4, and so forth. So that the natural frequency ratios are 2:1, 3:2, 4:3, 5:4, 6:5, etc. And the sounds that we hear, the pleasing sounds that we hear from plucked strings and also from vibrating air columns, will be made up of these ratios, and also some of the other ratios. 5:3 is natural because you can have the 5 and you can have the 3. 7:3, any integer ratios turn out to be natural. Okay, we just had a disaster, so we'll stop the tape here and go on in a minute.